You are watching the What's New with Motionworks IEC 3 video series. In this video, I'll demonstrate and explain the multi-axis mechanisms that the MPiec controller can operate using MECHATROLINK servos. Hi, I'm Matt Pelletier. Here's a quick preview. The MPiec controllers can use MECHATROLINK servos to directly control a variety of mechanisms, including gantries, H-bots, T-bots, and Delta robots. They are all set up using groups and the hardware configuration. Kinematic equations in the controller firmware produce multi-axis coordinated motion to control the servos of these specialized mechanisms. Now, let's look at this in more detail. The MPiec controller can use PLC Open Part 4 programming for virtually any type of multi-axis mechanism. So it's not limited to just gantries, H-bots, T-bots, and Delta robots. But whatever the mechanism, kinematic equations are required. These kinematic equations convert the positions in the coordinate workspace to positions of the servo axes that actually move the mechanism. These kinematic equations can reside in the application code of the MPiec controller, within some type of external controller, or within the MPiec firmware. In this video, we'll focus on mechanisms supported by the MPiec firmware, but let's consider briefly the case where kinematic equations exist in the application code. You start by using PLC Open Part 4 to program the coordinated motion in a virtual gantry mechanism. Then write kinematic equations in Motionworks IEC to convert the gantry positions to positions of the custom mechanism. The block Y Group Direct Control will send the converted positions to the individual servo axes of the custom mechanism. This method is very flexible and can be used for any mechanism, but it's also programming intensive, and it requires a thorough understanding of the mechanism in order to write the kinematic equations in the application code. Programming can be a lot easier if the kinematic equations exist in an external controller, such as the MLX200. You still start with PLC Open Part 4 programming, and the MPiec controller converts this programming to network commands, and the external controller coordinates the motion of the servo axes. This reduces the programming complexity, but it does require this external controller. For gantries, H-bots, T-bots, and Delta robots, we eliminate the external controller and the kinematics in the application code by including the kinematic equations in the firmware of the MPiec controller. You still use PLC Open Part 4 programming to produce coordinated motion, but the servo axes are controlled directly over MECHATROLINK. Details and options for these mechanisms are defined in the hardware configuration of Motionworks IEC. I'm using version 3.4. This MP3300 IEC project has a number of MECHATROLINK 3 servos. Below this, the groups are a collection of servo axes that control a particular mechanism. The group name is used to program the coordinated motion for that mechanism. Let's start by looking at the group for the gantry mechanism. You see the axes assigned to the mechanism as labeled in the diagram. You have probably seen something like this before. Actuator X moves actuator Y, and so the tool plate can move in 2 dimensions of Cartesian coordinate space. There are lots of variations and types of gantry systems, and technically there is no kinematic equation necessary for these. There are several options here. Under mechanism type, a 3D gantry adds the vertical Z-axis for 3 dimensions, and the N-dimensional gantry gives you this machine coordinate system button, and this way you can add axes that angle the tool, such as roll, pitch, and yaw. You have up to 6 degrees of freedom, and therefore 6 servo axes. Let's say we were controlling this gantry. You see the X-axis motor has a long shaft and drives 2 actuators at once. But it is also common to use a separate motor for each actuator. In this case, you would simply use add secondary axis. Both the primary axis and the secondary axis will be synchronized. Now on to the H-bot. The H-bot is a mechanism with two stationary motors driving a single belt. The belt is attached at one side of the tool plate and routed through a series of pulleys. If just one motor turns, the tool plate moves at 45 degrees. When the motors turn in the same direction, the tool plate moves in the X direction. When the motors turn in opposite directions, the tool plate moves in the Y direction. An H-bot is most often used in the horizontal plane with coordinates X and Y. However, you can also change that to X and Z and add a rotational axis to rotate the tool. Set kinematics lets you specify shaft rotational direction relative to the diagram. And mechanism type HBOT2 has the belt connection point at the opposite side of the tool plate. Graphically, there's just a very small difference between HBOT1 and HBOT2. But that difference is important for the kinematic equations inside the controller firmware. H-bots are an economical and stable mechanism capable of high speed and wide range of sizes, often used for path generation or pick-and-place applications. Very similar to the H-bot is the T-bot. The T-bot also has two stationary motors that drive a single belt, routed through a series of pulleys. And just like the H-bot, the T-bot's motors work together to move the tool plate in two dimensions. If just one motor turns, the tool plate moves at 45 degrees. When the motors turn in the same direction, the tool plate moves in the X direction. When the motors turn in opposite directions, the tool plate moves in the Z direction. T-bots are often mounted vertically for pick-and-place applications. And if this is the case, under machine coordinate system, you can exchange the Y-axis for Z, giving you an XZ system, and the optional rotation axis RZ. Set kinematics has shaft rotation definition for positive movement. T-bot style 1 has the belt attached at the tool plate. T-bot 2 has the belt attached at the top and a pulley at the tool plate. Like H-bots, the T-bot mechanism is an economical solution suitable for high-speed pick-and-place of medium loads over a wide range of lengths. A Delta robot has the base on the top and uses 3 motors. Each motor drives a base leg joined to a platform leg, and all the legs join at the moving platform where the tool plate is connected. Delta robots are exceptionally fast, especially with light loads, making them ideal for pick-and-place applications involving small parts. Yaskawa currently manufactures 2 Delta robots, the MPP3H and the larger MPP3S. Both of these robots have the option of the rotational axis at the tool plate, and use custom Delta if you have a third-party Delta robot with Yaskawa servos. In this case, use set kinematics to enter the critical dimensions of the mechanism. Collision and breakage can be avoided by establishing software limits that define the range of motion for each axis. In the case of the Delta robot, each axis has limits regarding the leg angle, speed, and acceleration. But these limits are distinct and defined separately from the limits of the tool moving within the Cartesian workspace. And that can be set here. This table shows the mechanisms currently supported for the MP3000 IEC series controllers. Delta robots, gantries, H-bots, and T-bots can be controlled at the firmware level by the MP3000 IEC series. Programming is the same for all mechanisms using PLC Open Part 4. If you want some hands-on experience with these mechanisms, check out our training class on robot control. Thanks for watching this video, and go to yaskawa.com/IECSW to download the latest version of Motionworks IEC 3.